Video title: Advanced Programming for Classical and Quantum Computing, Emerging Technologies and the Future of Programming. The rapid evolution of computer programming is being fundamentally reshaped by advanced emerging technologies, AETs. These include artificial intelligence, AI, assisted programming, quantum-aware software design, low-code and no-code development, agentic AI coding environments, and hybrid quantum classical algorithmic frameworks. The convergence of these technologies has created a new paradigm where human creativity, AI reasoning, and quantum principles coexist to redefine computational performance, scalability, and efficiency. Programming has historically evolved in layers, from machine code to procedural and object-oriented languages, and more recently, to data-driven and agentic systems. However, the next frontier lies in developing programming technologies that are adaptive, autonomous, and quantum compatible. This report explores these new frontiers, distinguishing their implications for both classical computing and quantum computing. Concept of advanced emerging technologies in programming. Advanced emerging technologies refers to systems and methodologies that transform software creation by embedding intelligence, automation, and multidimensional computation. Unlike traditional coding approaches, where programmers manually define every rule, AETs integrate automation, learning, and simulation directly into the development process. Key characteristics include autonomous generation and validation of code using AI models such as large language models, LLMs, and agentic systems. Context-aware optimization through meta-learning, reinforcement learning, and prompt-based software engineering. Quantum readiness, where algorithms are written in hybrid formats executable on both quantum and classical hardware. Cross-disciplinary modularity, linking mathematics, physics, AI, and systems engineering within unified programming ecosystems. These technologies accelerate software development cycles, reduce human error, and enable experimentation with computational methods once considered infeasible. Advanced programming for classical computing, AI-augmented programming. AI-augmented programming platforms, such as GitHub Copilot, Google Gemini Code Assist, and OpenAI's Codex, represent the most visible frontier of classical programming automation. They employ deep neural models trained on vast code corpora to predict and generate code snippets in real time. These systems use contextual embeddings that interpret the semantic intent of human instructions, transforming natural language into executable code. Developers can describe desired outcomes, and AI models autonomously produce syntactically correct, often optimized solutions. This integration of natural language processing and program synthesis has made programming more intuitive, accessible, and efficient. Low-code, no-code, and vibe coding environments. Low-code and no-code platforms, e.g., Microsoft Power Platform, Mendix, and Bubble, democratize software creation by enabling non-programmers to build complex applications via visual interfaces. Vibe coding, a conversational form of coding coined by Andrej Karpathy, extends this further. Developers interact with AI agents conversationally, describing functionality and logic while the AI implements them. These paradigms augment classical programming with automation pipelines and declarative logic generation, shifting the programmer's role from writing syntax to designing logic flow and evaluating outputs. Agentic AI systems for software engineering. Agentic AI represents a significant leap beyond static AI code assistance. In these systems, autonomous software agents perform coding tasks iteratively, testing, debugging, refactoring, and optimizing code in loops. Frameworks such as AutoGPT, SWE Agent, and MetaGPT are early manifestations of AI-orchestrated programming ecosystems. The resulting workflows integrate cognitive capabilities, reasoning, planning, and learning, allowing continuous improvement in large software systems. Such agentic systems can handle complex interdependent modules, crucial for building large-scale simulations, enterprise systems, or multi-agent digital twins. Advanced emerging technologies for quantum programming. Quantum computing introduces a fundamentally different model of computation based on the principles of superposition, entanglement, and interference. Programming for quantum systems demands new abstractions, mathematical representations, and hybrid integration with classical environments. Quantum programming languages and frameworks. Quantum programming languages such as Qiskit, IBM, Cirq, Google, Q-Hash, Microsoft, and Penny Lane, Xanadu, enable the development of algorithms executable on quantum processors. These frameworks provide libraries for quantum circuit construction, noise simulation, and hybrid quantum classical computation. Advanced emerging technologies are enhancing these platforms through quantum-aware compilers that optimize quantum circuits for limited-depth qubit architectures, AI-assisted circuit synthesis that learns efficient gate decompositions and error mitigation strategies, cross-domain APIs allowing quantum functions to be embedded in classical Python or C++ workflows, hybrid quantum classical programming. Most current quantum computers operate in a hybrid model where quantum subsystems perform specialized tasks, e.g., optimization, linear algebra, or sampling, and classical systems handle control, pre-processing, and interpretation. Emerging technologies now enable quantum classical interoperability through differentiable programming frameworks, e.g., TensorFlow Quantum, Penny Lane, that allow gradient-based learning of quantum parameters, quantum kernels that embed classical data into quantum Hilbert spaces for enhanced machine learning performance, quantum agents, AI systems capable of making decisions using quantum reinforcement learning, where policy updates are influenced by quantum probability amplitudes. AI-enhanced quantum algorithm design. AI's integration with quantum algorithm development is revolutionizing the discovery process. Generative AI models can explore large design spaces to create or optimize quantum circuits, search for Hamiltonians, or propose error-correcting codes. For example, reinforcement learning can train neural networks to design circuits with minimal decoherence or to adaptively control qubit measurements. These developments are bridging quantum computing and AI into a single adaptive system of quantum intelligence. Comparison: classical versus quantum programming technologies. Computation unit bit, 0 or 1, qubit, superposition of 0 and 1, programming language Python, C++, Java, Rust, etc. Qiskit, Q-Hash, Cirq, Penny Lane execution model. Deterministic, sequential, digital probabilistic, parallel, wave-based AI integration. Code assistance, LLMs, agentic systems. Quantum circuit synthesis, hybrid AI. Quantum agents. Error handling, debugging and software testing. Decoherence correction and noise mitigation. Application software engineering, data analytics, automation optimization, cryptography, molecular modeling, machine learning. The convergence of both paradigms is forming a hybrid computational ecosystem, where classical logic drives control and quantum systems perform exponentially complex calculations. Benefits and opportunities. The integration of advanced emerging technologies in programming offers transformative benefits. 1. Productivity acceleration. AI-assisted tools reduce development time, allowing rapid prototyping and deployment. 2. Algorithmic innovation. Quantum classical integration unlocks solutions to NP-hard problems previously unsolvable by classical computing. 3. Accessibility. Low-code and conversational programming lower entry barriers, promoting inclusivity in computational research. 4. System optimization. Agentic AI agents autonomously refactor and test code, improving reliability and energy efficiency. 5. Interdisciplinary expansion. Bridging quantum mechanics, mathematics, and AI promotes new research across physics, health, and finance. Challenges and future directions. While the potential is vast, significant challenges remain. Quantum hardware limitations. Qubits suffer from decoherence and error accumulation, requiring advanced error correction protocols. Explainability in AI-generated code. AI-generated software may contain opaque logic, raising concerns about accountability and security. Standardization and interoperability. Quantum programming environments lack universal standards, complicating cross-platform integration. Ethical and educational issues. Automated coding changes skill requirements, demanding reskilling of programmers toward algorithmic design and validation. Future directions include developing quantum-native AI agents capable of learning from quantum state spaces, expanding quantum software development lifecycles, QSDLCs, integrating version control, simulation, and verification, establishing international quantum programming standards for algorithm reproducibility, designing AI-driven meta-compilers capable of translating high-level classical logic into hybrid quantum code automatically. Conclusion: advanced emerging technologies are redefining computer programming for both classical and quantum domains. The integration of AI-augmented, agentic, low-code, and quantum-aware environments represents a shift from manual code construction to intelligent co-creation. In classical computing, AETs enhance automation, collaboration, and performance. In quantum computing, they enable new frontiers in computation, simulation, and problem-solving. Together, they lay the foundation for the next generation of computational intelligence, a hybrid paradigm where programming evolves into an interactive, adaptive, and quantum-empowered discipline. As universities, industries, and governments invest in this transformation, mastering advanced programming for both classical and quantum systems will become an essential competency for future scientists, engineers, and innovators.